Yesterday 12:42 p.m. Hello, I'm confused. I don't know how this is working, but do I get to save this after question mark? I don't know. It seems like it didn't pick up that I was asking a question. What if I ask another question? Interesting. What if I ask another question? This little eligibility, the baby, the ball. Yesterday 1:04 p.m. Or actually, thank you kids. I don't know. I like this. Or okay. So if we let AV be an interval in the real numbers and we like effects, the amount of information on it is the have made it be, then f is integral on a to b if this limit exists, okay. So for your purposes, write this theorem as state. The definition is given in sense to use the class because for our purposes, right, we can take that 11 star. We can take that to just be the right end point of each of the subintervals when we repeat that when we break up our integral from a to b in this other difference. Does that make sense? So right, this is for our purposes. Yeah, just take the right 3 months. Something the right hand side here, but the key is that it's actually more general than that. But yeah, and then right we have our object that we write the integral from a to b of f of x dx. So this is just our symbol that we use for that limit on the right hand side. So the result of the calculator going to get the function that we put inside of this symbol here in the middle here. This is called the integrand. So make sure you understand that when I say integrand, I mean this function that appears inside the integer, and again, this is our variable of integration. Now why it's connected to that dx there, we'll see later in class. Just r for the moment. Just look at that data and thinking going after that indicates our variable of integrations. But for the moment, just think of that dx as integrate as indicating that essentially our variable of integration is x, and then we have a lower bound of integration and an upper ground of test. Now, here's a theorem that I don't want to prove, but it's very nice. One says, if a function f of x is a continuous function on the interval from a to b, then f of x is integral on a to b. And in this case, when we put this square, so if we accept a continuous function, a nice continuous function on our interval, the integral is guaranteed to exist. Okay, and what that means is then we have this continuous function. All of the left to do is to calculate it because we know that the calculation will lead to a number. Okay. But since the integral is the area under the curve, if we actually know kind of the area of the shape made of the graph, we can avoid the whole limiting procedure and just compute it directly. Okay, so for example, right, let's look at this example. Once we wanted to calculate the value of the integral from 1 to 3 of x minus 1 dx, okay. But let's do this by kind of identifying what shape is, right. So here is the graph of x minus 1. Okay, and so if we consider the region from 1 pet 3, what kind of shape does the graph make over the x-axis triangle of triangle? Yep, in particular, this trying to this blue, this purple shade of triangle. Right, so you see that the area under our curve of x minus 1 from 1 to 3 is just the area of this purple triangle. So to compute the integral, we just need to compute the area of that purple triangle. We don't need to bother breaking stuff up into rectangles. We can just compute it directly. Okay, now our area of the triangle formula is that the area of a triangle is 1/2 times the base times the height. Okay, so for our problem, what is the base? And what is the height? 3 and 2 respectively. Yeah, 3 and 2 respect. I mean to and to differentiate, right? Yeah. So this is 2 times 2 equal to 2. So what we see is that therefore we can conclude that the integral from 1 to 3 of x minus 1 dx is equal to 2. Right. So in this one, right, we have a nice problem where there's a nice geometric interpretation for our integral. Any questions before? So what if we wanted to calculate this integral here of x plus 7 over 3 dx? Well, here I have a graph, right? So the area under the curve here, if we look at it between -1 and 2, right? So those bounds of integration -1 and 2. That means we're really interested in the area under the curve above. Different. So right. So the area under the curve of the region of above -1 to 2. Okay, so we can break this region up into the triangle and a rectangle. I guess if you're fancy you could use like the trapezoid area formula, but I like to just break it up. Yes, and so the area of the triangle is 1/2 phase times height. And the area of the rectangle is base times higher. So I'd like you to spend a minute or two trying to work through these calculations and see what you get for the end result here, and then I'll go over the answers. I think it's important for you to kind of think about problems, even if you're stopped before I go over the answer, because when you're thinking about the problem, you might notice where you get tripped upwards. To do, which shows you when it's over here able to compute the area of the triangle and the area of the rectangle. How would you determine the integral sum? Okay, just add them. So let's write. So over triangle, here is 1/2 and 3 times 1, which is 3/2 area of our rectangle. Here is 3 times 2, which is 6. And therefore we can conclude after some calculations that this integral is 50 1/2. Okay, so does this is clear here? Not. Starting up slow before I showed that nasty looking summation formulas there? Okay, so any questions? Okay, here's the another one. So here, what if we wanted to calculate this integral? Well, any ideas how we make about this? So we have that square. Yeah, we can start by saying with square root. It would sound good, that orientation. That was great. So on that, and then we can do the chain rule at it. Let's try something. But yeah, that would work probably. Yes, radicals, in sense of sideways parabola? Okay. Well, the radical 4 minus x squared. What does the graph of that look like? Don't you like it? I think I sell my yeah to send me circles. The top half of the circle, right? Because it's only defined unless you, okay, we pretend, it's only defined between negative 2x between negative 2 and 2. If you want to get fancy, you can define it outside there, but that's too fancy. Anyway, so here we have the top here, right? This is the graphing square, root of 4 minus x squared. And this is y of x is equal to negative 4 minus x squared. Okay, so if we want to, then shade the region of our graph of square, root of 4 minus x squared between 0 and 2. What part of the circle gets shaded? In top right corner. Yeah, the upper right corner is what we would shade and what we need to calculate the area of the compute. The integral here, right. So does anyone remember the area of the circle? Pi r square. So we've got our pi r squared here. So what's our r is 2. We have a circle, a gradient is 2. So we've plugged that in, we get that. This area is equal to pi times 4. So then, what is the integral here of the value of the integral? Pi, the value of the integral is pi. Remember to eat lunch beforehand. And now, same time makes me anyway. So we have piers here. So now we computed another integral in this one, right? If we wanted to kind of do it by breaking it up into rectangle, loop, 3, barely. Now soon, we'll come up with some more different formulas, but the moment I just wanted to show that, right? Well, often be breaking up and determining things by determining areas of various shapes. So, I just wanted to get people a little familiar with that at the moment before we go back into really trying to deal with computing. Integral of explicitly. Okay, so any questions before I move on? Okay, so here's something right. So now we'll be connecting kind of this 3 months. Something to some analytic forms. Now here I have a few formulas involving various sums. I'm going to go over the reasoning behind these if I have time at the end of class, but this first one, like sum from I equal 1 to end with I is equal to end on then plus 1 over 2. Well, there's this story that I think is made up about this mathematician named Gauss, as supposedly when he was in elementary school. He was being really annoying in math class, like asking a bunch of annoying questions that were beyond like where they were in class of the teacher, told them to sum every number between 1 and 100 out, and he on the spot gave the answer in any because he figured out this formula. Well, it's not that hard, right? You can consider it's n times and plus 1 over. I'll explain it anyway. Well, and in the next one there, the formula's like this for I squared and IQ. Okay, so in this case, let's try to use this definition to compute this integral from 2 to 5 of x, the x here. But to help you get started there, kind of 4 tasks to begin with that I think we should be able to handle, so give you a chance to kind of go through and try to answer from these 4 questions before I get the answer, and then I'll show how we can put it all together to actually compute an integral directly by taking a limit. Yeah, put some stuff on the right floor. It'll be useful later. Just to keep in mind, the stuff on the right is our formulas that we're going to use on the next day. But it's one of them up there so that you can start trying to remember, have them in your mind as you go through these square. What? I am with your problems. It's probably best if you try to write down. But even if you're just kind of thinking about how to get started or just trying to think about the problems, that all right. But try to write. You know, when you're writing them, you're going to want to leave that in variable. You want to leave it as something that's variable, so we can take, here's our delta x. It's just refuse that formula, right? We take the length of the interval that we're integrating over and we divide by n. Okay, and what is our f of x here? What's our integrated or integrand is just x. So what would the height of the function for the I of the interval using the right point tools? Get f of yesterday 1:20 p.m. using the right point tools. Yeah, f yesterday 1:20 p.m. using the right point tools. Yeah, f of x's. Yeah, exactly, would be just the x of I. So here is the explicit x sub I we use on this problem, and if we plug that into our f, well, we get the same thing because x, our function, just takes x and returns it. So now we just put this together into our being. On sum, everyone get what that's supposed to be saying? Maybe. Here, I guess when I transferred it messed up. There we go. Okay, so we have our x and we have our delta x, we just plug it. Okay, so now useful is right, we want to look at those formulas on the right hand side. You have 3 formulas, we know, for explicit sort of sums. So our next step is to try to make what we got out here look like something in terms of those sums on the right hand side. Okay, so any ideas? I just wanted to multiply it out and use some manipulations of the remarks, and here's what. Right, so here, right. So we have this formula here. So now we rewrite it one way. So just the first thing I do is inside the sum, right? I just distribute that multiplication and get this results right now. What I do is we have these two things in the sum. Well, it turns out that if we have a sum of two things, we can split that up into two sums and we can pull out common factors, right? So for example, we have so our left b sum here breaks up into 6 over n times the sum from I equal 1 to n of 1 and then plus 9 over n squared times the sum from I equal 1 to n of I. Okay, so now what do we do? Well, anyone know what the sum from Michael want to end up? 1 is so one of them that would be 1 times n. Okay, yeah, we look at this for something from 1 to any. So when we just have 1, we get a 1 for each value of I between 1 and 7 cents. So that first one we could just use n. And then that second term, we can use 9 number n squared times n plus 1 over 2. Okay, so now this is something that we can almost take the limit of 6 complex abs. Sorry that these should be on one line. So this should be 6 plus 9 tabs times 1 plus 1 over n squared. Okay, so now what do we do? Now we can take the limit, right? Because right, we didn't take our limit here because what does this limit and what happens when we take this limit? To get the integral. Yeah, we just so when we take that into infinity, right, most of nothing will change except that term involving and what happens to that term involving ants and things that 0 because the denominator is getting very big. So that means the fraction is getting closer and closer to 0. So when we take that limit, we just replace that 1 over n squared with 0. Now that's just a limit. We can evaluate by plugging it alternatively. If you didn't know how to rewrite this, you could take the limit of the top using towels. Yes? Okay. So are using their kind of rotation like frequently in the so. We'll use this notation frequently in driving solutions to simplified problems where there's some when we'll see a few of those kind of problems later. Okay, so we'll be using but often. If you're actually just computing things in terms of the computing integrals, we'll probably be using the antiderivative. But it's just we want to go through it at this level so that when we're like sometimes the things are admin together, we'll have some certain interpretation in an applic and then it will be important to understand kind of books. The other questions sounds very good. Okay, so now let's not give you a little bit of time to kind of try to set up the problem here to try to do this kind of computation. And here's you just need to identify what exide delta x are and then plug that into this formula here. And then what you'll want to do is try to again rewrite it using one of these sums. So this problem is barely challenging. So your first she really just be trying to figure out what this a right room on sum is just fun expression for it. Then the next step is just try to look for a patterns. Packages.com, so that's fine. Okay, so in this case radar. Delta x is for over n and these are our 11. So these are what you can plug in for 11 and that remain sum. And so there's everyone. And so at this point, how would you receive? Just multiply it out and then so each chairman that sum is multiplied by 3 over n cubed. So what we do with that via rank q? So if we wanted our thing to look exactly like one of those tornadoes, what would you do to the other side of the sum? Yeah, we can just every term in the sum is multiplied by 3 over n cubed, so they can hold that outside of the sum and we're just left with a sum that we know how to compute. So at this formula get there, right? So yeah, so just essentially plugged in instead of having that sum from IKEA 1 to n times I squared we plugged in times n plus 1 times 2 and plus 1 over 6, right? So many questions yet, so like the formulas in the top right. Is that just supposed to be making it easier for us to like do this summation and like in fractions that sort of or it's to make it possible? Yeah, right, because right, when you're taking limits, it's nice to have a very explicit formula. So it's a lot easier to take the limits. If we don't have any sums, any summations linear. Yeah, will we be doing this formula suppress? Yeah, I won't ask you to memorize that sort of thing. It must like it's a problem that you're really brought to the zoo. Yeah, these are just things to remember, but so the reason we're trying to doing this is a story if we will because before calculus as I've been invented, someone had already able to kind of go through these sort of calculations and figure this out. Like they could fall under. So right. So we're kind of showing you kind of what math was like before, how just was invented because that really makes things easier because then we can just take the indicator. So, but we're trying to kind of, but these sort of arguments were known before calculus was a thing of calculus made it gave a consistent way to do these kind of calculation. Okay, and so right. So we just did some algebraic manipulations so that our right 3 months. Sum has this particularly nice form, so that when we take that into limit as n goes to infinity, well, all those n's in the denominator, these returns that becomes 0. Okay, so the reason we started with some nice area things is that these things part of cars, but everything just kind of transmitter Sandals formula because it all helps later on. Go back to. So now here's an example of how we can actually use integrals in 3 months to do an interesting kind of problem, right? So what we want to do is we want to kind of approximate the area between the two graphs with any equal 20 rectangles by expressing it as a right removes them in sigma notation, and then calculating this the value, okay. You're just using a calculator, right? But so we have these functions gmx, which is 3x plus 4, and we have this function f of x, which is x squared, right? So we want to find the area of the region between them, how much we go about 2 of the area between them above that interval 1 before. So we have 2 patient calculated the area under both curves and then subtract them. Okay, so that's what we can do, right? And this is something called throughout the x. There is glass add that the x right at the end of that second formula, right? So we could write out the area under g of x between 1 and 4. So that would be our integral of 3x plus 4 dx, and then we could subtract the area under x squared. Okay. Now it turns out, we'll see later, that our integral has a nice property called linearity, which means we have this difference of integrals. But if we combine them, you just need to combine the ingredients, right? We can just combine the integrands, that makes sense. So this will be like an official property we'll discuss later after the moment. Just do it because it's a nice thing to do. Yeah, so you're saying the reason why we can combine them this way is because they're both from 1 to 4. Yeah, okay. Yeah, and you just look at the areas and the area of the shaded region. Well, that will be the difference between the area under g of x from 1 to 4 and the area under that orange per x squared. But now he set up our free modest sum. Right somewhere on the interval from 1 to 4, that length of the interval is 3. So that's why we have 3 over 20. You want to approximate it using a 3 months sum with pointy rectangles. Okay, and so now we set up this integral. We read off the 3 months sum, but in this case, we can always kind of evaluate these and check our work using that 3 months sum calculate. Yeah, fun shot would be wrong about the last sum is missing the delta x. It's otherwise, it's something enormous. Yeah, it's if you just left side of the entire Sunday, right? Yeah, I forgot to put this out today. So what we can do is we can just put it parentheses here and a parentheses here. Divided by, there we go. Now it's nice. So, it's questions. Yeah, is it like it's between? I mean, I should be here. 20 years, 20, the 20 comes from a year, right? And equal point, we're just giving it right, and it should be 3 over 20 seconds. Yeah, isn't just being odd, and it's 1. Plus, and inside that, yes, I have no idea what's going on. So, it all looks right to me. And so that makes sense. Yeah, so this is just comes from that formula for delta x. But I see I'm like to the reason I was putting that delta x formulas because I need to do it for myself. So anyway, so ready. So these are just 3 months. Some no little bit that we can just put this into every month somehow. Okay, so, and ignore that thing on the top, because we're in the top cons. There we go. So, here's every month, some calculator, and yeah, yesterday 1:37 p.m. And yeah, this, yesterday 1:37 p.m. That would match the top effect, is the top correct. Okay, any questions? Then, here's another kind of problem that we'll see later. So another kind of problem we could do is say you're manufacturing something on the lathe, right? Well, you want to make something that is symmetric about an axis, and you want to know how heavy that thing would be that you'll make. Well, if you know the density of the material, then if you can compute the volume, you can get the weight of that component, right? Anyway, but so here's the method to compute. The area under a core revolved around the x-axis. So what this revolution about the x-axis is, kind of think about the x-axis as the center line of the lathe. Well, then it will be, you take that shape and just spoiler. Grant, that makes sense. So you just take the shape under this curve and twist it around the x-axis. Now, if you don't fully get that yet, I wanted to just bring this up early so that it makes more sense when you have to go through the calculations later in class. Okay. But here, if we take a thin rich angle, so for each value of r, so the radius of these shape we get when we rotate about the axis will just be the radius will be f of x, right? So we want to do is now approximate the volume of a solid of revolution about the x-axis and equal 20 rectangles. Okay, and so we need to look at this thing where we want it. Just add up the volume here, right? So if we add up the volumes of these thin cylinders with wood, delta x will get the total volume, right? So if we use n equal 20 rectangles, well, then to find the area, we just need this. Sum up the voltmeter to find the total volume using this sum of the volumes up with the small draft, angles b sub t. Okay, it's about the volume of the rectangular rotated revolves around the x-axis, right? So we have a lot of little cylinders that we combine together 7x cents, and well. So if you want to combine that volume, and we just added the volumes of all the little cylinders. Now, r squared will send our function f of x determines the kind of the radius if we're thinking internally. Well then, where we see that r squared, we replace that with f of x k squared times delta x. We have this formula here. You can rewrite this formula as follows, and we see we just get every month sum in terms of a function. That's x squared plus 1, all of that squared, right, times pi, right. So when we sum of these behaves, notice that what we get at this end step here is just a 3-month sum. Okay, so if we wanted to put this into our 3 months sum calculator to approximate this sum, what would the function we'd put in the calculator feed? Yes, yeah, would be that a function that appears next to delta x, so in this case, right, our function would be pi and x squared plus 1 squared. And now here I couldn't get a nice picture of the graph of these volumes. But anyway, so we put this together and write. So see what this does is it just adds up the volumes of these rectangles. So now the function here represents the volume of each of those small cylinders that made up the final volume of revolution. Yeah, so this equation that you put in the calculator is like 2D representation of the cylinders. Yeah, last one tracked. Yeah, but now what the area of the rectangles on this graph are actually falling, okay. Because yeah, so any questions I know started off kind of slow and then kind of really sped up. If you're having some trouble juggling these sums, don't worry too much. It takes a while getting used to them, but feel free to stop my office. So now the last thing I want to do is bring up how we can actually get some of those sum formulas actually fall back. So I'll think of that first one. Alright, so we have this formula sum I is equal 1 to n, or of I, right? We have this sum, and we want to understand it. Well, let's look at a few examples so we could take any equal 100. So this is the problem that the Gauss's elementary school teacher supposedly gave him in this story. Okay, what does this sub mean? In the case, when n is 100, about great to just be 1 plus 2, plus 3 and plus 98 plus 99. First one here. Okay, now what's the first term plus the last journey number 1? What's the second term plus the second blaster 101.01? Yeah, website. I like these people 101. Right, so if you were to add all these up together, what would you get? 10,155. Yeah, because right, is it? No, it is right. We each think get paid off, right? But we'll get is equal to 101 times 50. That would be, okay, so 101 times 50. This would be 50 working on quadratin. Now this in other words, right, but this is 100. I mean 100 times, yeah, 1 request, over cube. Okay, so this series for in other words, right. This is an example that formula 10 have 1 plus 10 over 2 where n is equal to 100. Okay, when you've heard. So now this procedure clearly goes as you would think in the case when it's even, right? So this just comes from taking n over 2 1 plus n, okay. Because when we're taking that person, last we're getting 1 plus n and we get that n over 2. So, in other words, another way to write this could be n over 2 times 1%. So now, if there was an odd number, well, it would work everything. We get paired off until you got to be in. And that value you get the end would exactly be of anything. Another one, plus 1 over it 1 plus another, okay. So with yeah. So any questions? Think that's just a nice way to show why that cornmeal works. Yesterday 1:50 p.m. Yeah, really laugh again. Yesterday 3:58 p.m. Hello, 12:09 a.m. So this app just writes down everything that we're saying immediately. And so, if you were to say something after me, it would write down what you're saying is the same color. Yes, so, like if I need to say that, what do I need to say? As I saying about you, I've never been that passionate. No, you were talking about how you would never be. Like you'd never say the romantic things that you say, like you've never said those. Yeah, I've never, but it was like the first part that I couldn't figure out, like where that sentence started, like I love you, or it's real, or oh, that can figure that part out. I've never, that's the beginning. I've never, what? See, I've never felt that passionate. I've never felt that passionate, and that's true because I've never said anything that romantic ever in my life. Yeah, okay, instead. Bevar, you awake him now. I'm just reading back the transcript from class and it's really weird because it feels like I'm just reliving the moment. Why don't you just record them instead, transcribe? Yeah, I think I should record it first and then transcribe it so that I have both. You're right. My only issue with recording the audio is the files are big. Does he not record his lectures? No squared. Yeah, I think he said something about how he just doesn't want to just like another thing to remember. But yeah, it feels like time travel when I'm reading the transcript. Feels like I can rewind and remember. What do you think? Babe, I never mind. I think you're sleeping. Have you seen Clue with Adam Sandler? Oh yeah, didn't we watch it together? Clue, Adam Sandler. You need to put. Yeah, I meant Click. We stopped watching it, as it was really racist. Yeah, it was really racist. Yeah, it was also sexist and horrible. The transcript also notices when I'm laughing. That's really cute. And I was gonna go and I forgot. What was that? Oh yeah. I was gonna go upload something because I don't want to forget. Okay, well give me a kiss because door. Okay, always. Yeah,